Welcome back to the Deep Dive. Today we're diving into, well, one of the most essential challenges facing anyone trying to build, regulate, or just understand the next wave of intelligent systems.
And that challenge isn't really technological, it's linguistic. The speed at which AI has evolved across, completely different industries, from medicine to creative software, it's left everyone with a fragmented vocabulary.
Totally fragmented.
Hmm.
Technical teams are speaking one language, policymakers are speaking another, and it feels like nobody's using the same dictionary.
Exactly.
And that's why you came to us with this incredibly dense but absolutely critical piece of source material. It's a comprehensive, updated glossary of key terms specifically for AI governance.
Right. It synthesizes feedback from top governance experts.
Okay, let's unpack this. Our mission today is to use this glossary as our guide. We're going to try and build a shared language, one that spans policy, technology, and ethics, one term at a time.
And this is so much more than just reading definitions. This document is crucial because governance, assurance, risk management, they all rely on having really clearly defined concepts. If we can't agree on the difference between, say, misinformation and disinformation, or explainability and interpretability, effective policy is it's impossible. This deep dive gives you the vocabulary you need for any real discourse on AI governance.
So think of us today as your guides through this lexicon. We're going to go term by term, but we'll pause, we'll zoom in, we'll connect the dots. We're really going to focus on the implications of these terms.
Because knowing the technical definition is only half the battle.
Right. The other half is understanding why it matters for you, for your organization.
And just a quick note for those of you familiar with the privacy world, this is different from a general privacy glossary. There's overlap, of course, but this brings in terms that are totally unique to AI systems.
Like model architectures, adversarial risks.
Exactly. Things that are now totally central to policy discussions.
So we begin, fittingly, with a foundational pillar for any responsible system: accountability.
Accountability.
Yeah.
It's the obligation, the responsibility of everyone in the chain: developers, deployers, distributors, to make sure the system is ethical, fair, transparent, and compliant.
It's the ultimate stop sign for the algorithm did it defense.
That's a perfect way to put it, yes.
But wait a minute. If accountability needs traceability, making sure you can trace actions and decisions back to a responsible person, how on earth do we do that with these massive, opaque neural networks? I mean, does the complexity of modern AI just break that principle?
That is the governance tension of our time, and the source acknowledges it. Traceability is the core function, but it also implies that the entity, the organization, is accountable, not necessarily every single neuron firing.
So it's about the process, not the math.
It's about documenting the full life cycle, the data you used, the decisions you made during training, the oversight you have in place. Traceability in a simple decision tree is easy. Traceability in a 300 billion parameter large language model, well, that's a massive documentation and audit challenge.
Speaking of documentation, we need to talk performance. That brings us to accuracy.
Right. And accuracy is a purely technical measure. It just asks, how correctly does the AI system do its job? It's not an ethical concept itself, but
No.
It has huge ethical implications.
Of course.
As the source notes, low accuracy in something like medical diagnoses can be a catastrophe. You have to measure accuracy against the intended purpose.
Okay, now let's step into how these things learn. First up is active learning, or query learning.
So most models just passively eat whatever data you feed them. Active learning is different. The algorithm actually selects the data it learns from.
It's
very picky. It actively requests specific, high-value data points that it thinks will help it learn best. It optimizes the whole process and often means you need less data overall. It's like a smart shopper for information.
And a really relevant application of that smarter learning, especially for anyone listening, is adaptive learning.
Yes, adaptive learning is the practical application of that. It's about tailoring educational content, the pace, the style, the subject matter, to an individual student. The AI watches your performance and adjusts the curriculum in real time to optimize your learning experience.
Okay, here's where the technical gets immediately dangerous. Adversarial attack.
This is a huge safety and security risk. It's the intentional manipulation of the model, usually by feeding it malicious or deceptive input data designed to fool it.
And the consequences are?
Compromised performance, often in really unpredictable and dangerous ways.
Can you give us a concrete example of why this is so critical to prevent?
The source material gives a really stark one. Fooling a self-driving car's computer vision system. An adversarial attack could trick the model into seeing a red stoplight as green.
Wow.
And that isn't just a glitch, right? It directly impacts road safety. It shows the real-world life or death impact of a system integrity failure. This is why robust design has to account for malice, not just random error.
That potential for failure is magnified when systems can act on their own. Next is agentic AI, or AI agents.
These are systems built for high autonomy. They can make and act on complex decisions with very limited human oversight, pursuing goals with a lot of self-direction.
And the governance question there is obvious.
It's huge. Who is responsible when an autonomous agent makes a harmful choice? That's why this definition is so central to any discussion about liability and human oversight.
And those human checks bring us right to the governance structures themselves: AI assurance and AI audit.
So AI assurance is the big umbrella. It's the combination of all your policies, frameworks, controls, everything you use to promote safe and trustworthy AI. It includes risk assessments, certifications, all of it.
And the audit.
The AI audit is the specific check. It's the systematic review to make sure you're compliant and to find unforeseen risks early on, especially during development.
All of which feeds into the big organizational goal: AI governance.
Right. This is the whole system, the frameworks, the practices, the processes that an organization uses to manage and oversee its use of AI. It's about aligning AI with your objectives, ensuring responsible development, managing risks, and staying compliant. It's the operating manual for responsible AI.
Okay, before we move on, let's just quickly define the absolute basic building block: the algorithm.
The algorithm is the recipe. It's the computational procedure, the set of instructions designed to perform a task or produce an AI model. It's the structured method for turning inputs into outputs.
And the next distinction is so crucial for setting expectations: artificial general intelligence, AGI, versus what we actually have today.
AGI is still theoretical. It's the sci-fi ideal of an AI with human-level intelligence that can generalize across tons of different tasks. By contrast, pretty much every system we use today is narrow AI.
Designed for one specific thing.
Exactly, one specific thing like image classification or language translation, and that's it.
So in the broadest sense, what is artificial intelligence, AI?
AI is an engineered system that uses computational techniques like machine learning to automate tasks or simulate intelligent behavior. And a critical part of that often includes automated decision-making.
Which leads us to the difference between automated decision-making and autonomy. They sound similar.
They do, but the distinction is important. Automated decision-making is simply making a decision without a human involved. Autonomy is the system's ability to operate independent of human intervention, its capacity for self-direction.
Now we hit what might be the most critical complex governance term in the whole glossary: bias. And the source is very specific here, breaking it down into 3 types.
Yes, and we need to spend a moment here. You can't govern bias if you don't know where it's coming from. So first, you have computational bias, or machine bias. That's a systematic error that comes from the model's own assumptions or the data itself. It's a technical flaw.
Okay, and the second?
Second is cognitive bias. This refers to inaccurate human judgment. The distorted thinking that might creep in when humans are labeling the data in the first place.
And the third type, the one that gets the most regulatory attention.
That would be societal bias. This is the big one. It's systemic prejudice or discrimination against a group based on things like race, gender, or religion. When an AI system learns from historical data that reflects these biases, it doesn't just reflect them. It amplifies them.
And that becomes a direct risk to individual rights.
A huge risk. And the source points out a common entry point for this problem: selection bias.
So how you pick the data in the first place.
Exactly. If your data set underrepresents certain groups, or if it's based on historical data that reflects past discrimination, the model will learn that biased reality as fact. Governing bias isn't just about writing a policy. It's about getting your hands dirty and scrutinizing your data before you even start training.
We'll wrap up this first section with a technical fix for improving stability: bootstrap aggregating, or bagging.
Right. Bagging is a pretty sophisticated technique to reduce variance and improve a model's stability and accuracy. It works by creating multiple versions of the same model and training each version on a random subset of the data.
So you're not relying on just one model's opinion.
Precisely. You're relying on a diverse committee of models. This reduces the chance that one specific flaw in the training data will dominate the final result. It's a key technique for ensuring robustness. Okay, as we move into the next segment, we're shifting from those foundational principles to the messy reality of data, models, and risk management. We're going to see how quickly these technical terms become major governance challenges.
And we're starting with a really familiar application, the chatbot.
A chatbot is an AI system designed to simulate human conversation. It usually relies on natural language processing, or NLP, and large language models to interact with people. From a governance standpoint, the key thing is data.
The data it takes in.
Yes, chatbots often ingest sensitive personal information during customer service interactions, which means you need really stringent data handling policies.
Okay, moving to how models process that information. We have two core methods, classification and clustering.
A classification model, or classifier, is used in supervised learning. Its job is to sort data into predefined categories like, is this email spam or not spam?
And clustering.
Clustering is an unsupervised method. Here, the AI looks at unlabeled data and groups things together based on similarity. It finds structures that you didn't explicitly tell it to look for.
Now for a quick but essential definition, compute.
Compute is just the physical processing power, the CPUs, the GPUs, the memory, the storage that you need to run these huge models. Without massive amounts of compute, modern deep learning just doesn't happen.
And a major field that uses all that compute is computer vision.
This is the field that's all about processing and analyzing visual inputs like images and videos. The governance implications here are massive.
Because it powers facial recognition.
Facial recognition, object detection in self-driving cars, deep medical imaging, all of it.
So we have these models. How do we make sure they're actually following our rules? That's the conformity assessment.
Right. This is a critical governance check. It's an independent analysis to verify that the AI system meets all your requirements. Risk management, data governance, cybersecurity. It's the formal check that confirms the system is operating safely.
And that structural check is vital for an individual user's right to contestability or redress.
Contestability is the principle that AI decisions have to be challengeable by humans. If you, the listener, get a negative automated decision, say you're denied a loan, you have to have a way to question it and get a human to review it. And that ability depends entirely on transparency.
Before we train anything, the data needs structure. Let's define the difference between a corpus and a counterfactual.
The corpus is the huge raw collection of text or data that's used to find patterns. It's the bedrock for large language models. A counterfactual, on the other hand, is a hypothetical alternative. It's a what-if scenario.
How is that useful for governance?
It's essential for auditing fairness. If an applicant was denied that loan, you can run a counterfactual analysis. You ask the model, what if we change just one variable, like their zip code? Would the outcome change? It helps you pinpoint the exact inputs that led to the rejection.
Okay, now let's talk about what happens when data goes bad, starting with data drift.
Data drift is a performance problem that hits models after they've been deployed. It happens when the new data coming in starts to change over time, consumer behavior shifts, new slang emerges.
So it no longer looks like the data the model was trained on.
Exactly. And when the model drifts, its performance tanks because the patterns it learned are no longer relevant.
Then we have more acute security risks, like data leak and the very malicious data poisoning.
A data leak is usually accidental. It's the exposure of sensitive data because of bad security, human error, something like that. It's passive. Data poisoning, however, is active and malicious.
It's an attack.
It's a full-on adversarial attack where false data is intentionally injected during training to corrupt the algorithm. The goal is pure sabotage, to make the model produce dangerous or misleading outputs.
And to fight these problems, we need rigorous tracking of data provenance and high standards for data quality.
Right. Data provenance is the logbook for your data. It tracks the entire history, where it came from, how it was collected, how it was changed, to ensure integrity. And data quality is the measure of whether that data is fit for use. Is it accurate, complete, consistent?
And we have to emphasize this for everyone listening.
We really do. If your data provenance is fuzzy or your data quality is low, your AI system is fundamentally unreliable. Garbage in, garbage out. It's that simple.
Okay, moving to some deep technical concepts. A simple but effective one is the decision tree.
A decision tree is a supervised learning model that looks like a flowchart. It visually represents decisions and their potential consequences in a clear, branching structure. The great thing about them is they're highly interpretable. You can literally see the decision path.
And the powerhouse behind most modern AI, deep learning.
Deep learning is the subfield that uses artificial neural networks models with many, many layers that are incredibly powerful for processing complex, raw data. It's what drives fields like NLP and advanced image recognition.
We're now facing this huge challenge of synthetic media and information integrity. We have to be very clear on the difference between deepfakes, disinformation, and misinformation.
Yes, the intent is everything here. Deepfakes are the tool, the audio or visual content that's been altered using generative AI.
And disinformation.
Disinformation is content created intentionally to cause harm. Bad actors use deepfakes to spread disinformation. Misinformation, on the other hand, is false content that is unintentionally misleading. It's spread by people who lack malicious intent.
And governance has to respond differently to an accident versus a targeted campaign.
Absolutely.
Let's define a key tool for creating generative content, the diffusion model.
Diffusion models are a type of generative model mostly used for creating images. They work by starting with pure, noise-like TV static, and then step by step they refine that signal, transforming it into a realistic image based on your prompt. That iterative process is why their outputs are so incredibly photorealistic.
We mentioned them before, but let's formally define the discriminative model.
Right. This kind of model maps input features directly to class labels. Its job is to analyze patterns to distinguish between classes, like telling a cat from a dog. It's all about analysis, in contrast to generative models, which create new data.
From analysis to uncertainty. Entropy.
Entropy is a statistical measure of unpredictability or randomness in data. In a prediction model, higher entropy means there's greater uncertainty in the outcome.
And that's useful information for an overseer.
It's critical information. If your model's output has high entropy, you know its certainty is low, and that's when a human needs to step in.
Before modern AI, we had the expert system.
An expert system is an older form of AI. It draws inferences from a pre-programmed knowledge base to replicate a human expert's decision-making in a very specific field, like medical diagnosis. The source uses this to draw a sharp contrast with AGI expert systems are narrow and can't reason generally.
And now for perhaps the most critical term for building trust, explainability, XAI.
Explainability is the ability to describe how an AI system came to a specific decision or generated a particular output. It's absolutely fundamental for transparency and trust. If you can't explain the decision, you can't check if it's fair or correct.
And that focus on checking starts before you even train the model, with exploratory data analysis, EDA.
EDA is what data scientists do before training. They use techniques to identify patterns, outliers, and relationships in the data. It's essential for spotting things like selection bias or data quality issues before they contaminate your model.
And finally, because things can always go wrong, we need fail-safe plans.
Fail-safe plans are your backup. They are the governance measures and technical redundancies that kick in if the AI system starts behaving in unexpected or dangerous ways. They're critical for robustness, ensuring that if the automated system fails, a reliable backup takes over immediately.
All right, our next segment brings us right up against the ethical requirements and the, frankly, enormous power of generative systems. We're starting with fairness.
Fairness is an attribute that's all about ensuring relatively equal treatment of individuals or groups by an AI system. The key governance requirement is that the model has to identify and stick to an appropriate standard of fairness.
But that's the hard part, isn't it? Fairness is a human concept. It depends on context. How do you measure it?
That's the tension. And there are dozens of statistical definitions. Does optimizing for one definition, say, equal false positive rates across groups negatively impact another, like equal false negative rates?
And the answer is often yes.
Often, yes, you are trading off statistical definitions. So, governing fairness requires making explicit policy choices about which groups and which metrics matter most for that specific use case. It's a negotiation, not just a technical fix.
Okay, next up is a privacy-enhancing technique that's getting a lot of attention, federated learning.
Right. Federated learning lets you train models across lots of decentralized devices, like individual phones, using their local data. But crucially, the raw, sensitive training data stays on the device.
It never goes to a central server.
Exactly. Only the model updates, the learned parameters and weights, are sent to a central location to be combined into a global model. It's a powerful way to enhance privacy while still learning from diverse data.
Now let's talk about the engine of the current AI revolution. The foundation model.
Also known as general-purpose AI or frontier AI. These are the huge, large-scale models trained on unbelievably vast and diverse data sets. This gives them broad capabilities in language, vision, reasoning, you name it.
So they serve as the base layer.
They're the starting point for countless specialized applications. Think of it as a massive general-purpose brain that you can then customize for specific jobs.
And that customization process is called fine-tuning.
Fine-tuning is when you take that massive foundation model and you train it further on a much smaller, highly specific, labeled data set. This makes the general model an expert in a niche area, like medical billing or a particular type of legal research.
And the ultimate test of any training, fine-tuned or not, is generalization.
Generalization is everything. It's the model's ability to take the patterns it learned from its training data and successfully apply that knowledge to new, unseen data. If a model can't generalize, it's essentially failed. We'll touch on this again later when we talk about overfitting.
So specifically, what is generative AI?
Generative AI is the subfield that uses deep learning to create new content, text, code, images, music. Unlike discriminative models that just classify existing data, generative models predict what comes next to create something novel.
But this power introduces unique risks.
Absolutely. Risks like deepfakes, and the one we'll get to in a moment, hallucinations.
Let's talk about an optimization approach that can be a bit of a trap, the greedy algorithm.
A greedy algorithm is one that makes the immediate best choice at any given step, based only on the information it has right then. The problem is it doesn't consider the long-term global best solution.
It's short-sighted.
Very. It chases the best short-term reward, which can lead to a suboptimal or even dangerous outcome overall. Governance needs to make sure these aren't used in situations that require complex, long-term strategic planning.
When we're training and testing, our benchmark for reality is the ground truth.
The ground truth is the objective, known, real-world state of a data set. It's the definitive reference point. If the model says an image is a cat, but the ground truth label says it's a dog, the model is simply wrong.
And now for that specific risk that makes generative models so hard to govern, hallucinations.
Hallucinations or confabulations are when these generative models create outputs that sound plausible but are factually incorrect. They'll fabricate sources, make up legal cases, report false historical facts.
And the danger is they do it with such confidence.
Exactly. They present these fictions as if they are facts, which makes trust and safety evaluations incredibly complicated.
Given all these risks, the philosophical approach has to center on the user. This leads us to human-centric AI.
This is a design philosophy that explicitly prioritizes human well-being, autonomy, and values. The goal is to build systems that amplify and augment human abilities, ensuring the tech serves people rather than undermining or controlling them.
And the practical way to enforce that is with human-in-the-loop, HITL.
HITL is a critical design pattern. It means incorporating human oversight, intervention, or control into the AI systems process. It's that mandatory checkpoint where human expertise or ethical review is applied, ensuring the system never operates completely unsupervised when the stakes are high. Okay, we've laid the ethical foundation. Now we need the formal processes for checking all of this and the technological engine that drives modern AI language models.
We mentioned risk assessment earlier, but let's formally define the process of an impact assessment.
An impact assessment is the evaluation process you do before deployment. It's designed to identify, understand, and mitigate all the potential ethical, legal, social, and economic implications of an AI system.
It's proactive due diligence.
It is. It ensures risks are addressed up front, not after something has already gone wrong.
Once a model is trained and deployed, it enters the inference phase.
Inference is the process where a trained model uses new, unseen data to make predictions or decisions in the real world. This is where all that training either pays off or fails.
And the fuel for the whole system is the input data.
Right. Input data is the raw data you feed the algorithm to produce an output. It is the entire basis for machine learning. We have to keep stressing the importance of data quality here. Flaws in the input will guarantee flaws in the inference.
Oh, let's tackle that crucial distinction we mentioned at the top. Interpretability versus explainability, XAI. They sound so similar. How does the governance lens separate these two ideas?
This is a great one to clarify. So explainability, or XAI, is about providing an explanation after the model has already made a decision. It's a justification.
A post hoc rationale.
Exactly. Interpretability, on the other hand, is about designing the model to be inherently understandable from the start. Its reasoning can be understood just by looking at its structure or features.
So an interpretable model is clear by its very nature, like a decision tree. But for a complex model like an LLM, which is inherently clear, you need explainability to provide a rationale.
Precisely. The source notes that high interpretability often requires a lot of domain expertise to design, and it's very domain specific. It's harder to build, but it gives you greater clarity from the get-go. And governance has to decide which is appropriate for a given use case.
The technical star of the show right now is the large language model, LLM. Let's go deep here.
LLMs are a type of AI that uses deep learning, pre-trained on text datasets so massive they're hard to even comprehend. They learn the statistical patterns between words and phrases to perform incredibly complex text-based tasks.
And what makes them large? Is it just the data?
It's the data, but it's also the model's capacity, which is measured by its number of parameters, often billions, sometimes trillions. That huge capacity is what allows it to capture all the subtle, complex relationships in human language.
And the source points out there are two main functional types of LLMs.
Right. You have generative LLMs, which predict what word comes next in a sequence. This is what you see when you ask it to write a story. Then you have discriminative LLMs, which focus on classification, things like sentiment analysis or text categorization.
And all of this falls into the broad category of machine learning, ML.
ML is the core subfield of AI. It's all about algorithms that iteratively learn from data to make predictions, building a model from that training data without being explicitly programmed for every single rule.
It powers everything from fraud detection to our streaming recommendations.
Everything.
And the final output of that process is the machine learning model.
That's the artifact. It's the learned representation of all the patterns in the data. It's what gets created by the algorithm, and it's what's ultimately deployed to make predictions on new data.
We defined disinformation as intentional harm earlier. Let's just quickly reiterate misinformation.
Misinformation is false content that is unintentionally misleading. The lack of malicious intent is the key differentiator. The policy response has to be different, even if the content itself looks similar to disinformation.
Okay, finally, let's turn to the transparency documents used to explain how a model works, starting with the model card.
A model card is a short document, like a nutrition label, but for a single AI model. It details its intended use, its performance metrics, and, crucially for governance, how it was evaluated across different conditions, like different cultures or demographics.
So it's a mandatory transparency tool for responsible deployment.
It should be. It provides essential context about the model's limitations and potential biases.
All right, in this next segment, we're exploring how models go beyond just text, what happens when training goes wrong, and the critical security steps needed before anything goes live.
Starting with complex inputs, multimodal models.
These are models that can process more than one type of data or modality at the same time. For instance, it might take in an image and a text caption and then produce a single output, like a score.
They're incredibly versatile, and they enable really complex tasks like advanced speech recognition or generating captions for images.
The engine that lets computers understand our language is natural language processing, NLP.
NLP is the subfield of AI that helps computers understand, interpret, and apply human language. It lets machines read, analyze sentiment, translate. It turns unstructured language into structured data.
And the fundamental architecture that makes all of this deep learning possible is the neural network.
Neural networks are models that sort of mimic the brain's neurons. They use multiple processing layers, including hidden layers, to model really complex, nonlinear relationships in data. They are central to every advanced application we've discussed today.
Okay, moving to a big policy consideration for deployment, open source software.
Open source software gives everyone free access to the source code, which promotes transparency and innovation. However, the source points out a major governance challenge here, which is open source models are often more lightly regulated than proprietary ones. This creates a risk of downstream misuse that developers and the community have to anticipate.
Now for the most common technical failure you have to guard against, overfitting.
Overfitting is a critical failure where the model becomes too specific to its training data. It essentially memorizes the test instead of learning the concepts.
And when that happens, it loses its ability to generalize.
Completely. It becomes useless on new, unseen data, which makes its real-world predictions inaccurate and totally unreliable.
To mitigate overfitting and all these other risks, organizations need rigorous oversight.
Oversight is the effective monitoring and supervision of an AI system. This isn't a one-time thing. It includes continuous monitoring, certification processes, and ongoing conformity assessments.
Deep inside the model are the variables that store all this learned information, the parameters and weights.
The parameters are the internal variables the model adjusts during training. The weights in a neural network are a perfect example. They store the learned information, and they're the mechanism the model uses to make predictions.
We can split the data workflow into a few main stages. First, pre-processing.
Pre-processing is everything you do to the data before training. Cleaning it, handling missing values, encoding it. We can't emphasize this enough. Pre-processing is where data hygiene happens. It's your best chance to mitigate bias and improve performance before you even start.
Then, after the model has run, you sometimes apply post-processing.
Right. Post-processing involves steps you take after the model has made its predictions to adjust the outputs. For example, you might tweak the model's predictions slightly to make sure they meet specific fairness metrics or business rules.
As interacting with these models becomes normal, we all need to understand the prompt and prompt engineering.
The prompt is just the instruction you give the AI to get an output. Prompt engineering is the art and science of carefully crafting that prompt to influence the model's behavior, to get more desirable outputs and minimize the chance of it generating something harmful or just plain wrong.
Let's talk about another algorithm that uses that committee approach we discussed earlier, random forest.
A random forest is a supervised learning algorithm that builds multiple decision trees using random subsets of data. That's the bagging technique again, and then it merges their results. This makes the final prediction much more stable and accurate, especially with complex or messy data sets.
And now, for a non-negotiable governance check, red teaming. This is more than just security testing.
It is. Red teaming is security testing with an adversarial mindset. You're not just checking for bugs, you're actively trying to break the model.
You're simulating real-world attacks.
You're trying to jailbreak it, push it to its limits, find its hidden biases and security flaws. The results of a red team exercise are non-negotiably used for fixing the model before it ever sees the public. It's stress testing for malice.
Let's turn to a complex learning paradigm that's been key to aligning LLMs with human values. Reinforcement learning, RL, and RL with human feedback, RLHF.
Okay, so RL on its own trains a model through trial and error. It learns to optimize its actions in an environment based on rewards and penalties. Think of training an AI to win a video game. No labeled data needed, just a goal.
And what does the human feedback part add?
RLHF integrates human input into that process. Humans will rank different outputs from the model, and that ranking provides an additional, really important source of rewards and penalties. This is essential for aligning the AI's behavior with nuanced human preferences and ethical values. It's how you teach it not to be toxic or unhelpful.
And the ultimate goal of all these checks and balances is reliability.
Reliability is the attribute that ensures the AI behaves as expected, performing its job consistently and accurately, even when it's faced with new or challenging data.
Another technique to make generative models better, retrieval augmented generation, RAG.
RAG is a way to enhance generative AI by letting it pull information from an external, trusted source, like a secure, up-to-date document library, when it's generating a response.
So it's not just relying on its training data.
Exactly. This dramatically increases accuracy and helps reduce hallucinations because it forces the model to base its answers on verifiable external facts.
We often focus on the software, but let's quickly acknowledge robotics.
Robotics is the field that allows AI software to interact with and control the physical world, designing and programming the machines that perform physical tasks.
And finally, for this section, we have robustness.
Robustness is the system's ability to be resilient, to withstand security attacks, including those adversarial attacks we talked about. A robust system keeps working correctly even when it's being actively threatened or fed corrupted inputs.
We are in the final alphabetical stretch now, focusing on system safety, security risks, and that non-negotiable requirement of transparency.
And we're starting with the big one, safety.
Safety is a really broad term. It covers minimizing AI, harms, misinformation, deepfakes, hallucinations. But it also involves mitigating malicious use and preventing some of those bigger existential risks that might come from advanced foundation models.
And for organizations, a major unmanaged risk is shadow AI.
Shadow AI is the unauthorized use of AI systems inside an organization. This is when employees go around the official policies and use tools that haven't been vetted, exposing the company to huge legal and operational risks.
We've covered supervised and unsupervised learning. Now for the hybrid, Semi-supervised learning.
This technique is a blend of both. It trains the model on a huge amount of unlabeled data and a small amount of labeled data. This is really crucial for generative AI because finding massive, fully labeled data sets is incredibly hard and expensive. This makes the training process much more efficient.
We detailed LLMs, but given the focus on efficiency in the source, we have to talk about small language models, SLMs.
SLMs are the smaller, more efficient counterparts to LLMs. They have fewer parameters and need smaller training data sets. Their big advantage is that they're ideal for deployment in places with limited compute power, like on your phone. They're faster and more accessible.
Okay, let's detail the most common training method of all, supervised learning.
In supervised learning, the model is trained on labeled input data, where you already know the correct output. It uses these examples to learn the relationships. This is what you use for classification grouping data or regression, which is about predicting values.
And when you don't have enough real data to train on, you can use synthetic data.
Synthetic data is data that's artificially generated by a system to mimic the statistical properties of real data. It's used when real data is limited or too sensitive to use, like in healthcare. It's a key way to train models while protecting privacy.
We talked about the model card for one model. The next level up is the system card.
A system card discloses how multiple AI models work together in a network. This is so important because many complex apps rely on different models talking to each other. The system card helps explain that whole interconnected process.
Finally, let's solidify the 3 core data buckets you use in any ML project: training, validation, and testing data.
The training data is what you use to teach the model. The validation data is used during the training process to check performance, tune the parameters, and, importantly, prevent overfitting.
And the final gatekeeper,
The testing data. This is used at the very end to evaluate the final trained model on data it has never ever seen before. If it performs well here, you can be confident in its ability to generalize.
an efficiency booster that builds on past work, is the transfer learning model.
This is when you learn one task like recognizing cats, and then you use that knowledge as a starting point for learning a related task, like recognizing dogs. It speeds up the learning process by not starting from scratch every time.
And the architecture that really revolutionized modern language models, the transformer model.
A transformer is a neural network architecture that's amazing at keeping context over long sequences of data, like a full paragraph. It does this using a technique called attention, which lets it focus on the most relevant parts of the input. This is absolutely essential for how LLMs work.
The ultimate governance goal for building trust is transparency.
Transparency is a broad principle about openness and accountability, but the source gives us 3 distinct meanings to think about.
First, it's about making information available to stakeholders, disclosing that AI is being used, maybe using watermarking and providing those model and system cards. Second, it's about maintaining good documentation for auditing.
And the third.
In the open source world, it means making the source code itself publicly accessible. And there's a constant tension there between transparency and the security risks that come with making your code public.
Closely related is trustworthy AI.
Trustworthy AI is often used interchangeably with responsible AI or ethical AI. It's about principle-based development, making sure you're upholding security, safety, transparency, accountability, privacy, and non-discrimination.
Historically, the whole idea started with the Turing test.
Alan Turing's original test was about a machine's ability to have a written conversation that was indistinguishable from a human's. It set that early benchmark for simulating intelligent behavior.
We talked about overfitting. The opposite problem is underfitting.
Underfitting is when the model fails to capture the complexity of the data at all. It's too simple. This results in poor predictability, usually because you didn't use enough features or parameters.
And the last major learning type is unsupervised learning.
This is when you train a model on an unlabeled data set with minimal human supervision. The AI just looks for patterns and inherent structures in the data on its own. It's great for tasks like clustering data or detecting anomalies.
Let's do quick definitions for 2 statistical terms we use all the time: variables and variance.
Variables, or features, are just the measurable attributes in your data set. Variance is a statistical measure of how spread out your data points are. High variance can lead to overfitting, which highlights that fundamental trade-off. Reducing a model's complexity reduces its variance, but it can increase its bias.
And to promote transparency in what AI creates, we circle back to watermarking.
Watermarking is the process of embedding a subtle, computer-detectable pattern into AI-generated content. This allows for clear detection and labeling of AI content, which is essential for transparency and fighting disinformation.
The very last term in our glossary, weights.
The weights are the learned information stored inside the model's parameters. They get adjusted over and over during training, and they're what the model ultimately uses to make predictions. They are the mathematical embodiment of the model's experience.
So after all that, what does this all mean? We have successfully navigated this really challenging terrain. We've covered the lexicon from accountability and agentic AI all the way to watermarking and weights. We've established a shared language for AI governance.
And the knowledge from today is that critical bridge. It connects the high-level policy talks with the on-the-ground technical challenges. You now understand the mechanisms of risk, like adversarial attacks and data drift, and you also understand the ethical imperatives, like measuring fairness or ensuring contestability.
This glossary really proves that AI governance isn't a siloed discipline. It requires a synthesized understanding, connecting the technical to compute the parameters, the weights, with the ethical goals of transparency, reliability, and human-centric AI.
And this knowledge lets you engage with this material not just as a consumer, but as an informed participant. You can now ask the crucial questions. Are we mitigating bias in pre-processing? Are we using red teaming rigorously enough? And this raises an important final question for all of us.
Right. The source defines small language models, SLMs, as being optimized for efficiency and limited compute.
Yeah.
So given the rapid advancement of these massive foundation models and the ongoing risks of things like hallucinations and data poisoning, how will that focus on efficiency in SLMs challenge or enhance the core AI governance principles of safety and robustness in the coming year?
Will the rush for faster, later models come at the cost of essential checks?
Or will they introduce new, more localized and reliable forms of AI? This is a fundamental challenge for the future of deployment that we all have to be prepared to navigate.